ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರಗಳು. ಇಂದಿನ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮದಲ್ಲಿ ಡಾಕ್ಟರ್ ಪಿ ನಾಗರಾಜ್ ಸರ್ ಅವರು ಥರ್ಮಲ್ ಪ್ರಾಪರ್ಟೀಸ್ ಆಫ್ ಮ್ಯಾಟರ್ ಎಂಬ ವಿಷಯದ ಮೇಲೆ ಉಪನ್ಯಾಸ ನೀಡಲಿದ್ದು, ಅವರನ್ನು ನಮ್ಮ ಈ ಒಂದು ವಿಜ್ಞಾನ ತಂತ್ರಜ್ಞಾನ ಇಲಾಖೆ ಅಕಾಡೆಮಿಯ ವಿಜ್ಞಾನ ಪ್ರತಿಭಾ ಶೋಧನೆ ಯೋಜನೆಯ ಈ ಒಂದು ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ಸ್ವಾಗತಿಸುತ್ತಿದ್ದೇವೆ. ವೆಲ್ಕಮ್ ಟು ಸರ್.
ಥ್ಯಾಂಕ್ ಯು ಸರ್. ಥ್ಯಾಂಕ್ ಯು.
ಸೊ ಅದೇ ರೀತಿ ನಮ್ಮ ಅಕಾಡೆಮಿಯ ಅಧ್ಯಕ್ಷರಾದಂತ ಪ್ರೊಫೆಸರ್ ಅಯ್ಯಪ್ಪನ್ ಸರ್ ಅವರನ್ನು ಕೂಡ ಸ್ವಾಗತಿಸುತ್ತಾ, ಹಾಗೂ ನಮ್ಮ ಮುಖ್ಯ ಕಾರ್ಯನಿರ್ವಹಣಾಧಿಕಾರಿಗಳಾದ ಡಾಕ್ಟರ್ ರಮೇಶ್ ಸರ್ ಅವರನ್ನು ಕೂಡ ಸ್ವಾಗತಿಸುತ್ತಾ, ಹಾಗೂ ನನ್ನ ಎಲ್ಲ ವಿದ್ಯಾರ್ಥಿ ಮಿತ್ರರು ಸಹೋದ್ಯೋಗಿಗಳನ್ನು ಕೂಡ ಸ್ವಾಗತಿಸುತ್ತಾ, ನಾನು ಕಳೆದ ಹಲವಾರು ಉಪನ್ಯಾಸಗಳನ್ನು ಡಾಕ್ಟರ್ ಪಿ ನಾಗರಾಜ್ ಸರ್ ಅವರು ಕೊಟ್ಟಿರೋದ್ರಿಂದ ಅವರ ಬಗ್ಗೆ ಈಗಾಗಲೇ ಕಳೆದ ತರಗತಿಗಳಲ್ಲಿ ಅವರ ಕಿರು ಪರಿಚಯ ಮಾಡಿಕೊಟ್ಟಿದ್ದೀನಿ. ಸೊ ಈಗ ನೇರವಾಗಿ over to you, sir.
Okay, sir. Thank you. Good afternoon to all dear students. I hope that you have already gone through this chapter. I don't think you have any doubts, but still I will explain some of the concepts regarding the thermal properties of matter. If you have any questions or clarifications, if you feel that something is to be modified or something is to be again explained, you can definitely contact me through KSTA. So anyway, I am thanking the organizers, especially the chairman, Professor S. Ayyappan, and Professor A.M. Ramesh. And with their, of course, permission only, I am going to talk to you. And again, I am telling you that I am going to talk on the thermal properties of matter. I am sure that all of you are familiar with the thermal properties and matter. First, what do we mean by thermal? Thermal means basically heat. And properties, you know, the characteristic properties, what happens to the materials when they are heated, whether what happens when the temperature is increased to the materials. To the materials, I mean it may be a solid, liquid, or gas. So how the liquids, when they are heated, different from that of solids and also from that of gases. This is what we basically understand under the chapter thermal properties of matter. When we say matter, it includes, like what I have said already, solid, liquid, and even gas. And all of us have felt heat in some sense or the other. But we should know what is heat. You know that there are many types of energy, something like mechanical energy, light energy, magnetic energy, electric energy, nuclear energy, and heat energy. And heat energy is one of the important concepts in our discussion here today in this class. Of course, I am not going to talk much about the mechanical energy. But anyway, the mechanical energy can be classified into two types, kinetic energy and potential energy. And basically, the kinetic energy is nothing but the energy which is in motion. That means the kinetic energy is due to its motion, whereas the potential energy, the other form of energy under the mechanical energy, is the potential energy. The potential energy is by virtue of its motion, position. Yeah, that's what. The kinetic energy is due to its motion, whereas the potential energy is due to its position. Thus, we divide, we classify the mechanical energy into the kinetic energy and the potential energy. For example, like what we observe, a moving vehicle has an energy, and that energy is called the kinetic energy. And on the other hand, a stone may be on the top of a hill, and it also has the energy, and that energy is actually called the potential energy. In fact, you can give number of examples for kinetic energy as well as potential energy. I am not going to give you number of examples with respect to kinetic and potential energy. In fact, you are already familiar with that. But as one or two examples I am giving like this. What happens when the substances are heated? When once the substances are heated, they expand on heating, of course, except with water, especially from 0 to 4 degrees Celsius. We will discuss even the expansion of water at the end. But anyway, when the substances are heated, in general, all substances expand on heating except water, especially between 0 and 4 degrees Celsius. Suppose we place a body on a fire, it acquires energy and it becomes hot. What may be the reason that it acquires energy? It is basically due to the molecular motion. And when we place it over a fire, yeah, here I am showing what happens to the molecule. Like what I have already said, that heat is a form of energy and it can be identified with kinetic energy of the molecules in motion. You see that the molecules are not moving in a systematic, or in other words called regular. In fact, the molecules move in a random motion or random fashion. So if one molecule move in the forward direction, the other one may be moving in the backward direction, something like that. So the motion of these molecules actually constitute the heat. And because these molecules are in motion, and therefore we say that heat energy is due to the kinetic energy of the molecules in motion. So at the molecular level, the random motion of molecules in substances, they generate heat. That's why I'm referring to this figure. This figure 1 shows that the molecules are moving in random fashion. So anyway, when the molecules are in motion, the heat generates heat. And it is also called thermal energy. The heat energy, in other words, called the thermal energy. The molecules of a substance are in a state of rapid motion. That is what I mentioned already. And I may even say that they are moving, vibrating to and fro. To and fro, that means if they are moving toward the wall and again they may be moving back. And this is what, suppose you think of a container like what I have shown in the diagram. The molecules may be moving toward the wall and then they were moving backwards. And that is why it is called to and fro motion. Whatever it is, the molecules are in a state of rapid motion, and these rapid motion of the molecules generates heat. Then like what I have already mentioned, the substance may be a gas, a liquid, or a solid, the particles of which are in restless motion. It doesn't mean that some particles will be at rest and some particles only in motion. All the particles will be in motion. And that is why we say that the restless motion. The sums of the energies of all these particles constitute heat energy. In fact, whatever the energy or whatever the motion, and each one will constitute the energy, and the sums of all the energies constitute heat energy, or in other words called the thermal energy. As the heat increases, the motion of, in other words, as heat increases, the motion of the molecules increases, or even the motion of the molecules increases, the heat increases. And that is why we say that vice versa. That means increase in heat results in increase in molecular motion, or increase in molecular motion due to some sense or the other, then the heat correspondingly increases. And that is why it is called the increase in heat and increase in the molecular motion is nothing but vice versa. Then coming to degree of hotness or coldness of a body is called temperature. Suppose the question is, what do we mean by a temperature? The temperature is nothing but the degree of hotness or coldness of a body. It denotes let me just, it denotes the thermal condition of a body. And two bodies at the same temperature may possess different quantities of heat. Let me repeat, two bodies at the same temperature. I mean here the temperature maybe, let us say, we may have two bodies and both of them may have the same temperature like 25 degrees Celsius or 30 degrees Celsius. But a body at a higher temperature always gives to a body at lower temperature, irrespective of the actual heat contents of the two bodies. Yeah, this is what you have to remember. Two bodies at the same temperature may possess different quantities of heat. A body at higher temperature always gives heat to a body at lower temperature. I mean, let us say you have some rod. When it is heated at one end, the other end of the rod is not heated, but actually the heat is transferred from the hot end to the cold end. That is in the same body. But even if you take one body, let us say, for example, we have fire and we may be standing just in front of the fire. We feel hot. That means heat is transferred from the hot body to the cold body. In the sense, again, we will have three types of transfer of heat, like conduction, convection, and radiation. I am not going to talk about what conduction is or what radiation or even the convection, but these are the three processes of heat transfer. The heat may be transferred from one body to the other by some means, but in most of the cases, even though if you don't touch the body, the heat may be transferred by means of radiation. So thus, the temperature is the state which determines the direction of flow of the heat from one body to the other. The average kinetic energy of the molecules of a body is an indicator of its temperature. Larger the kinetic energy, higher will be the temperature. And remember, temperature is only the degree of hotness or coldness, whereas heat is a form of energy and temperature is only a level which indicates at what temperature or at what level it is. Thus, heat is the cause and temperature is the effect. So causing the temperature is nothing but the heat. This is what heat is the cause and temperature is the effect. Suppose we want to understand the basic difference between this temperature and heat. As I already said, heat is a form of energy and temperature is the measure of degree of hotness. It is the cause. Heat is the cause and temperature is the effect. And it is the sum of energies of all the molecules, whereas the average kinetic energy of the molecules gives the temperature. So it is a measure, it is measured in joule. Heat is measured in joule, whereas temperature is measured in Kelvin, that is in SI. But you are already familiar with three different units of temperature. One is degrees Celsius and another one is Fahrenheit. And degree Celsius can be converted into Kelvin. In fact, it was Lord Kelvin who established this unit, and that is why we use this Kelvin scale. I tell you something about Kelvin scale after 5-6 minutes. The direction of transfer of heat does not depend on the quantity of heat, whereas the direction of transfer of heat depends on the temperature. If the temperature is higher in one body and lower on another body, the heat flows from a body at higher temperature to a body at lower temperature. This is what I said in the beginning itself. And coming to this measurement of temperature. Yeah, like what I have already mentioned about three different scales, and temperature is measured by an instrument called thermometer. So the name of the instrument which measures the temperature is the thermometer, which is based on the principle of heating effect. Like what I said earlier, if we heat a substance, the substance expands except water. That's what I said in the beginning. So increase in volume is one such effect. And in fact, Galileo was the first person to invent a thermometer on this principle. What is that principle? Increase in volume actually causes the increase in temperature, or first person about the heating effect. Later, thermometers were developed based on the expansion of mercury on heating. I am just showing you different types of thermometer. Here is a clinical thermometer, and clinical thermometer you are familiar with, especially under the clinical thermometer. You know our body temperature, normal human body temperature is 98.4 degree Fahrenheit. And if you convert that degree Fahrenheit into Celsius, it comes out to be 37 degrees Celsius. But actual calculation shows that 36.9. And that is why the range of the clinical thermometer in terms of degrees Celsius is from 35 to almost 42 degrees Celsius, because our normal human body temperature is about 98.4. Sometimes we may even write it as 98.6, but usually it is 98.4 degree Fahrenheit. And when it is converted from the Fahrenheit to degrees Celsius, it comes to be 36.9, or we say about 37. And coming to the next one, yeah, this is what we have, the laboratory thermometer. And laboratory thermometer you have used in the laboratory, especially to measure even the ambient temperature. The ambient temperature is nothing but the lab temperature and even the room temperature, or even when you measure outside the room, that is normally called the ambient temperature. Usually, we use what is called a laboratory thermometer. The laboratory thermometer is basically from minus 10 degrees Celsius to 110 degrees Celsius, and it has been divided into 100 equal divisions. So even though the range is from minus 10 to 110 degrees Celsius, but there are 100 divisions in the sense totally it is minus 10 and then 120, but it is divided into equal parts, 100 divisions. So in the laboratory thermometer, or even you call it as the clinical thermometer, you have the bulb here. And there is a slight difference between the laboratory thermometer and the what is called the clinical thermometer. In any case, we are using mercury. I hope you know why we are using mercury. The reason for using the mercury doesn't stick to the glass. On the other hand, if we use water, it will stick. And we also think of what is called the cohesive force and the adhesive force in respect of water. So here in mercury, the other important factor about why we use mercury in a thermometer is the density of mercury is very high. It is of the order of 13,600 kg per meter cube. And even the surface tension is more than that of water. So that is the reason of using mercury either in the laboratory thermometer or in the clinical thermometer. Sometimes even alcohol thermometer is also available. Even alcohol thermometer is also used in the laboratory, but normally we use mercury thermometer rather than alcohol thermometer, because if we leave the alcohol thermometer, some break will be there inside the fluid, and that is why better we use the mercury thermometer rather than alcohol thermometer. But anyway, alcohol thermometer visibility is very good compared to the mercury thermometer, but still we normally go for the mercury thermometer. So on the other hand, if we have what is called the maximum and the minimum thermometer, in case if you want to go for the maximum and the minimum minimum temperature in a day, Say morning, if you keep on recording by one thermometer, again in the evening, it is rather too difficult to keep the measurement accurately about the maximum and the minimum thermometer. On the other hand, if you use a thermometer like this maximum and minimum thermometer, in fact, it keeps giving you what is the maximum temperature in a day in the morning and then the temperature in the evening. So this is what the construction of the maximum and the minimum thermometer. I am not going to give you the construction of this because there are other things to discuss rather than this. And that is why I am just sticking to this. So coming to the next one, converting Celsius, Fahrenheit and Kelvin. You should know that Celsius scale of temperature proposed by Anders Celsius in the year 1742. It is expressed in degrees Celsius. Fahrenheit scale temperature proposed by Gabriel Fahrenheit in the year 17. Oh, I think there is some mistake in this. It's not 17, it is something different. Let me just, I think, no, it is in 1724 only. And this, of course, Kelvin scale of temperature was proposed by Lord Kelvin in the year 1884. This is what we have on different thermometers. Yeah, sorry, I did a mistake. Let me go back to this 1742. Yes, Celsius scale of temperature proposed by Anders Celsius in the year 1742, whereas Gabriel Fahrenheit in the year 1724, and Kelvin's it is in the year 1884. I think better, yeah, already I have written down, but I said wrongly. So 1742, 1724, 1884. So this is what the year the different types of thermometers have been proposed. And coming to the, for example, any thermometer for that matter, we take the freezing point of pure water. In Celsius scale, we take it as 0 degrees Celsius, Fahrenheit 32 degree Fahrenheit, and in Kelvin, it becomes 273 Kelvin. Boiling point of pure water is taken as 100 degrees Celsius. Remember, it is only at the sea level and not at any higher altitude. And in Fahrenheit, the 212, that is the highest, 32 is the lowest. And similarly, Kelvin means 373. If you add 100 to 273, it becomes 373. And temperature of human body, I have already mentioned with respect to the clinical thermometer. There I have shown that as 36.9, but approximately we write it as 37 degrees Celsius. I mentioned that it may be 98.4 and 98.6 is written here, but usually it is 98.4 and 310 Kelvin. So the relation between the Celsius scale and the Fahrenheit scale is obtained like this, because in degrees Celsius 100 divisions are there, and we take it as C minus 0, because to start with it is 0, and in Fahrenheit it is F minus 32, and this conversion comes to be like this. Coming to the next one, of course, the absolute 0 or 0 Kelvin scale corresponding to minus 273 degrees Celsius. It is rather too difficult to reach such a low temperature, minus 273 degrees Celsius. Any temperature T degrees Celsius is related to the Kelvin scale by capital T is equal to T plus 273. In fact, if you want to convert degrees Celsius into Kelvin scale, we add 273. On the other hand, if you want to convert from Kelvin scale to degrees Celsius, we subtract 273. And that is how in Kelvin scale, we put it as some T degrees Celsius plus 273. Suppose there is a question like this. Let us say there may be a question like, what is the temperature at which a Celsius and Fahrenheit reading will be the same? And in fact, this question is normally asked in many interviews or in many what is that entrance examinations, including IAS. If you look into IAS preliminary examination, some in old question paper, this question is there. And in many questions, entrance examination, this question is very common. That means at what temperature the Celsius and the Fahrenheit reading will be the same. In order to find out, like what it is already mentioned, we use C over 100 and F minus 32 over 180. And let us take that C is equal to X is equal to F. That means C is equal to F is equal to X means X over 100, F minus 32 over 180. And if you simplify this, you get minus 40. So minus 40 is the temperature at which the Celsius and Fahrenheit reading will be the same. So the boiling point of water is at 100 degrees Celsius. What is its value in Fahrenheit scale? Yeah, you will get 212. Already I have mentioned it. The normal human body, how you convert, this is what you have, like 98.6 minus 32. And this calculation is very simple. You can anyway, before we go for the thermal expansion, let me just tell you only in brief about what is Boyle's law. And Robert Boyle, that was in the year 1627 to 1691, who is an English chemist. Charles law. But what is that Boyle's law? Pressure of a given mass of gas varies inversely as the volume when temperature is constant. That is P proportional to 1 over V, or P is equal to, rather P into V is equal to a constant. Normally for pressure we use small p, and for volume we use capital V. Therefore, I have taken here P into V is equal to a constant. And on the other hand, Charles law states that the volume of a given mass of gas is directly proportional to the temperature when the pressure is constant. Or the pressure of a given mass of gas is directly proportional to the temperature when the volume is constant. So V by T is equal to a constant, or P by T is equal to a constant, which was introduced by Charles in the year 1747 to 18, who actually lived in this range, French scientist. And based from Boyle's law and Charles' law, we are able to get another law. That is what we call it as the ideal gas law. And that is PV by T is equal to a constant. And that is nothing but the ideal gas equation. In general, PV by T is equal to NR, or PV is equal to NRT, where N represents the number of moles, where R is the universal gas constant, and its value is 8.31 joule per mole Kelvin. And let us now understand the thermal expansion. What is that thermal expansion? Like what I said in the beginning, all substances expand on heating and contract on cooling. So increase in temperature increases the dimension of a body, which is called the thermal expansion. There are actually three types of expansion. One is linear expansion, the other one is aerial expansion, and the third one is the cubical expansion. What is this linear expansion? If the substance is in the form of a long rod, then for small change in temperature, we may call it as delta T. And delta T is nothing but T2 minus T1. If you call the initial temperature is T1, it may be 25 or 30 degrees Celsius, whatever it is. Then higher temperature is T2. Higher temperature need not be very high of the order of 100 degrees Celsius. Even if we say 25, 30, 25 is taken as T1 and 30 degrees Celsius may be taken as T2. So T2 minus T1 gives you delta T. The fractional change in length is written as delta L by L, which is equal to alpha delta T. Delta L by L proportional to delta T, and where the proportionality constant is alpha, where alpha is the coefficient of linear expansion. Thus, we can define alpha is delta L over L delta T. In other words, the coefficient of linear expansion is defined as the ratio of increase in length per degree Celsius to its original length per degree Celsius, or even you can say per Kelvin. Whether you talk in terms of per degree Celsius per Kelvin, it is same, because 1 degree change in temperature, whether you measure in degree Celsius or in Kelvin, both will be the same. That is not that 25 degrees Celsius is equal to 25 Kelvin. If you want to convert 25 degrees Celsius to Kelvin scale, you have to add 25 to 273. And that is what I am telling here is 1 degree Celsius means, let us say the temperature changes from 25 to 26. So 25 to 26 means the change in temperature is 1 degree Celsius. Accordingly, we can write it as 25 as 288 Kelvin. 288 Kelvin to 289 means 1 Kelvin. That is why the range of 1 degree Celsius is equal to the range of 1 Kelvin. But not that 1 degree Celsius is equal to 1 Kelvin. So if the substance is in the form of a square, then we write it as delta A by A is equal to B delta T. That where beta is actually the coefficient of areal expansion. And in fact, beta can also be written as delta A over A delta T. The coefficient of areal expansion is defined as the ratio of increase in area to its original area per degree Celsius rise of temperature. So if the substance is in the form of a cube, then delta V over V delta T, and that is actually, yes, what I have written here is only delta V by V, no delta T here. You can just note down this correction. So it is delta V by V is nothing but gamma delta T, where gamma is the coefficient of volume expansion. So here I have made it correct. Gamma is equal to delta V over V delta T. So in the previous one, that is delta T is there on the left as well as on the right. That is wrong. It is only delta V by V is equal to gamma delta T. On the other hand, gamma is equal to delta V over V delta T. So coefficient of cubical expansion or volume expansion. The volume expansion, in other words, also called the cubical expansion, which is nothing but the increase in volume to its original volume per degree Celsius rise of temperature. So coming to this, let us say that coefficient of linear expansion and the coefficient of cubical expansion or volume expansion. And I am going to show you that the coefficient of areal expansion beta is equal to 2 times the linear expansion, coefficient of linear expansion. Similarly, the coefficient of cubical expansion is equal to 3 times the linear expansion. But I have not listed here the coefficient of areal expansion. I have only listed about the coefficient of linear expansion and the coefficient of volume expansion. For example, if you take aluminium in the form of a rod or thin wire, it becomes 2.5. Remember, the power is 10 raised to minus 5 per Kelvin. And 2.5 into 10 raised to minus 5. You have to read that as 2.5 into 10 raised to minus 5. The power of 10 remains the same, 10 raised to minus 5, even in volume expansion. But the numerical value will change from 2.5 to almost 7.4. In fact, it is 2.4 something, and that is how we are getting 7.4 here. And similarly, if you take brass in the form of a thin wire or rod, it is actually 1.8 into 10 raised to minus 5, but here it is about 6. If you ask me a question that you said that gamma is equal to 3 alpha, that is the coefficient of volume expansion is equal to 3 times the coefficient of linear expansion. Here I have written as alpha 1.8, but gamma is written as 6. It is more than even 3 times. But anyway, the approximate value is given here. Iron, it is again in the form of wire, 1.2, and gamma value 3.5, copper 1.7, and this comes to be 5, silver 1.9, and cubical expansion is 5.2, glass, Pyrex, it is 0.32, and 3 times means approximately 1. We cannot think of the linear expansion for mercury, and that is why we have only the volume expansion, or volume expansion becomes 18.2 into 10 raised to minus 5. Similarly, water. So this is what you have the relation between alpha, beta, and gamma. If you want to go for beta, 2 times this. That means aluminium 2.5 into 2 becomes 5, 5 into 10 raised to minus 4. Similarly, for any material you take here, it is 2 times. So I think you can do it by yourself. When once you know, if you could remember the value of alpha, you can get the value of beta as well as gamma. So coming to this, there is a simple relation between the coefficients of alpha, beta, and gamma. That's what I said in the beginning. That is, beta is equal to 2 alpha and gamma is equal to 3 alpha. How to show that beta is equal to 2 alpha? And I already said in the beginning that delta L is equal to alpha L delta T, and delta A is equal to that beta A delta T. And this is what change in area, we can write it as L plus delta L whole square. That means if you take initially the length of the wire as L, the increase in length becomes delta L. Instead of that, you can even write it as L2 L1. Then alpha can also be written as alpha is equal to L2 minus L1 over L1 into T2 minus T1. That is the another way of writing it. But here again, if I want to show that delta A, I put it as L plus delta A, L plus delta L whole square, because you know if it is in the form of a square, then area is nothing but L square if it is a square. So L plus delta L whole square minus L square, that is the original length, original area rather. So if you expand that L plus delta S, it is in the form of A plus B whole square, A square plus B square plus 2AB. Yeah, exactly in the same way here, L square plus 2L delta L plus delta L square minus L square. L square cancels, and delta L square is negligible. When delta L itself is small, naturally delta L can be further small and therefore it can be neglected. Thus we will get it as 2L delta L. Therefore delta A is equal to 2L delta L, and beta is equal to delta A over A delta T. You just substitute. So 2L delta L over A is L square delta T. Thus it becomes 2 delta L over L delta. One L cancels. You have only L in the denominator, and thus beta is equal to, because it is delta L over L delta T is nothing but alpha, and thus beta is equal to alpha. On the other hand, if you want to show that delta V is equal to L plus a volume, you know, if you take it in the form of a cube, then cube means it is length equals breadth is equal to what is that, height. So if all the three are equal, then we denote it by L itself. In that case, we write it as L plus delta L whole cube minus L cube, and this is L cube. Yeah, if you remember what you have got the formula in algebra, A plus B whole cube is nothing but A cube plus B cube plus 3AB into A square plus B square. That formula, if you remember. So exactly in the same way, you can write L cube delta L cube 3L delta L plus delta L, and minus L cube means L cube cancels. You will have 3L cube delta L by L, and this 3V, and that is how we get gamma is equal to delta V over V delta, and thus we get it as gamma is equal to 3 alpha. So this is what we have the relation between alpha, beta and gamma. Already I have mentioned that alpha is the coefficient of linear expansion, beta is the coefficient of areal expansion, and gamma is the coefficient of volume expansion or cubical expansion. And thus we know that beta is equal to 2 alpha and gamma is equal to 3 alpha. And that is, in other words, we can even write it as alpha is to beta is to gamma equals 1 is to 2 is to 3. So that also we can verify whether alpha equals beta equals gamma equals 1 is to 2 is to 3. So this is what we have in the form of a solid. Yeah, only with respect to a solid, we can think of the alpha, it is coefficient of linear expansion, beta, areal expansion, and gamma, that is the volume expansion. But in respect of liquids and gases, you cannot think of alpha and beta, we can only think of gamma, that is the volume expansion. When we go to liquids, especially we have two types again, apparent expansion and real expansion. But before I come to that, I will take up this liquids. Under the liquids, I am especially discussing with respect to anomalous behavior of water. What is this anomalous behavior of water? Yeah, I told you already, except water, all substances, whether liquid or gas or even solid, expand on heating. And especially water contracts on heating between 0 and 4 degrees Celsius. That means instead of increase in volume between 0 and 4 degrees Celsius, there is decrease in volume. Because there is decrease in volume, the density increases, especially from 0 to 4 degrees Celsius. Instead of increase in volume, the volume of water decreases. And from 4 degrees Celsius onwards, it behaves like any other liquid. So its volume increases with increase in temperature. But only between 0 and 4 degrees Celsius, there is some anomalous behavior. So as volume, in other words, if you go from 4 degrees Celsius to 0 degrees Celsius, if you take like this 4 to 0 degrees Celsius, volume increases, whereas density decreases. You should not have any confusion. If you go from 0 to 4 degrees Celsius, volume decreases, density increases. If you are talking in the reverse way, that means if you go from 4 to 0 degrees Celsius, volume increases, whereas the density decreases. Thus, the density is maximum at 4 degrees Celsius. So temperature at 4 degrees Celsius correspond to the point of maximum density. And this property has an important environmental effect. How this anomalous behavior of water is significant, especially in cold countries. In cold countries, as the temperature approaches freezing point, that is 0 degrees Celsius, the ice forms on the surface of water in lakes and rivers. Even though it is on the surface, it is ice, and water at 4 degrees Celsius has maximum density. It goes down below the surface of ice, enabling fishes and other aquatic species to survive. In case, right, if everything is ice, then the aquatic life would not be possible, and in a way, the anomalous behavior of water is advantageous for the aquatic life or aquatic species to survive. If water did not have this property, lakes and ponds would freeze from bottom up, which destroy much of their animal and plant life. So this is an important point to be remembered. And now I am just showing you the graphical representation, especially at 4 degrees Celsius, what I mentioned earlier, the density is maximum, it goes down. As we go from 4 degrees Celsius to 0 degrees Celsius, the volume increases. As volume is increased, naturally the density decreases. If you are coming from 0 to 4 degrees Celsius, the volume keeps on decreasing till it reaches 4 degrees Celsius. But from 4 degrees Celsius onwards, it increases like any other liquid. And especially between 0 and 4 degrees Celsius, it shows a peculiar behavior. And this peculiar behavior of water is called anomalous expansion. And like what I have mentioned already, that at 4 degrees Celsius, the density is maximum. And this is what density is maximum. It is shown in the reverse order in this. So variation of volume and density of water with temperature is shown here. And yeah, coming to gases, I mentioned about gases. Gases expand at ordinary temperature more than solids and liquids. For an ideal gas, the coefficient of volume expansion at constant pressure can be found from the ideal gas equation. If you talk about the gas, again, when the temperature is increased, in fact, even though I don't have written here, I can just mention that Q proportional to m theta, or in other words, Q is equal to Cm theta. That means the quantity of heat is directly proportional to the mass and the increase in temperature. Suppose you remove the proportionality constant, then you will write it as Q is equal to Cm theta, where C is the specific heat capacity of the material in general. For example, if you talk in terms of gases, we have two types of principal specific heat capacities. One is the specific heat capacity at constant pressure, and the other one is the specific heat capacity at constant volume. So we denote it by Cp and Cv. What is that? Cp, that C and P is the lower case, that is subscript. The specific heat capacity at constant pressure is defined as the ratio of that definition, of course, you know already. Then suppose I go for how Cp greater than Cv. In fact, at constant pressure, the work is done, whereas at constant volume, no external work done. If we supply the heat to a gas at constant volume, whatever the heat which is supplied, it is used only to increase the internal energy of the gas molecules. Whereas in the case of a pressure, a constant pressure, the heat supplied to the system or supplied to the gas uses in two ways. One is to increase the internal energy of the gas molecules, and the other one is to supply the external, what is that, external work done. So thus, in fact, we can even write is like R is equal to Cp minus Cv. Cp is greater than Cv. This is the usual question in respect of gases. That is why Cp is greater than Cv. Because at constant pressure, the heat which is supplied is utilized to increase the internal energy of the gas molecules as well as the external work done. Whereas in the case of Cv, that is constant volume, whatever the amount of heat which is supplied is utilized only to increase the internal energy of the gas molecules. So this is what I don't go further because some 5 minutes time is required for you to maximum 10 minutes for you to ask questions or clarifications or comments on this. So shall I stop at this or can I go further, sir? Hello?
Sir? ಹೇಳಿ sir.
And one more thing that I would like to mention at this contact in this program. See, for example, gases will not be, for example, hydrogen is not an ideal gas at all temperatures. And why? because if we keep on cooling, like what I said in the beginning, in general, substances expand on heating and contract on cooling. Suppose you cool the gas, for example, hydrogen becomes a liquid at minus 240 degrees Celsius, or in other words, 33 Kelvin. So at 33 Kelvin or minus 240 degrees Celsius, it becomes a liquid. And I hope you remember, especially the helium, the liquid helium temperature is 4 Kelvin. It is almost minus 269 degrees Celsius. That means no gas is ideal. And even if you just think of nitrogen, the nitrogen becomes a liquid at minus 146 degrees Celsius. You yourself can find out what would be the liquid nitrogen temperature in terms of Kelvin. And similarly, the oxygen the oxygen becomes a liquid at minus 183 degrees Celsius. If you want, you can calculate. It comes to be about 50 Kelvin. Like this, no gas is an ideal gas. When do we call it as an ideal gas? A gas is ideal if it behaves as an ideal gas at all temperatures, because normally the gases become liquid at a particular low temperature, and that is why we cannot have an ideal gas equation, rather ideal gas. But still we talk about what is called an ideal gas equation. That's what I said in the beginning, that PV is equal to nRT, or PV, suppose we take N is equal to 1, we call it as PV is equal to RT. This equation holds good only when the temperature is high and not when the temperature is low. That means this equation cannot be valid, especially when the gas behaves as a liquid. Yes, sir. Anything more? Shall I stop at this, or further can I go further?
You have to take another 5-10 minutes, sir.
Okay, sir. Yeah. So suppose we want to calculate, for example, gamma is equal to 3 alpha. This is what here I have mentioned. For an ideal gas at 0 degrees Celsius, gamma is equal to 3.7 into 10 raised to minus 3 per Kelvin. And like what I have already mentioned, that you may have some problem. And let me just tell you only in brief about some problems. I will pick it out. I thought that you have questions rather than problems. And that's why I thought that let me not go to the problems. But still, because you have problems also on this. And that is why just only 1 minute time. Give me. I have the problems. Yeah, for example, if I take a problem like this, because, for example, if I go for, I should also make a mention before I go for the problems about what is called the isothermal expansion, adiabatic expansion, or isothermal change, adiabatic change, isochoric change, isobaric change. So only after that I can give you the numerical problems, only after discussing about the isothermal change. What do we mean by an isothermal change? If the change is taken place at a constant temperature, then we call it as an isothermal change. That means either the heat is system means, for example, you have, anyway, you will be studying later in thermodynamics about the source, sink, and insulating stand. The source, for example, you have a cylinder, and normally the cylinder consisting of a something like in the form of a container, and that bottom of the container is perfectly conducting, whereas the sides of the container perfectly non-conducting, and it is provided with a piston, and the piston is again perfectly non-conducting. Like what I told you about the CPCV that we can think of in respect of this. And isothermal change means, let us say the volume of the gas or volume of what we have in the container is constant. If it is constant, then the piston will not move up. When the piston doesn't move up, then there is no work is done on it. And that is what we call it as an isothermal change. And suppose we can also have what is called isothermal expansion or isothermal compression. Isothermal expansion means the piston goes up, and in that case, we will have what is called thermal expansion. And if the piston comes down, thermal compression. And remember, in a thermal compression, the heat is produced, whereas in expansion, the temperature decreases. On the other hand, in compression, the temperature increases. So in expansion, the temperature decreases, whereas in compression, the temperature increases. I think you don't have any confusion with respect to that. So expansion, temperature decreases, compression, temperature increases. And isothermal change, adiabatic change means there is no transfer of heat between the system and the surrounding. So no transfer of heat means, suppose we put the container on an insulated stand, then there is no transfer of heat between the system and the surrounding, means environment, outside. Either you keep it on the source or keep it on the sink, then there is transfer of heat between the system and the surrounding. But only when it is kept on the insulating stand, there is no transfer of heat. So in a isothermal change, we talk about PV is equal to RT, whereas in an adiabatic change, we say about PV to the power of gamma is equal to a constant. That is in an adiabatic change. When we say PV to the power of gamma is equal to a constant, where gamma is actually the ratio of specific heat capacities. So gamma is equal to Cp by Cv. That is the ratio of principal specific heat capacity at constant pressure to the principal specific heat capacity at constant volume. So based on that, we can have some problems. And one problem, rather than taking as a problem, I don't know whether you could be able to calculate. Anyway, I will just take up one problem like this, and that problem could be in an isothermal expansion. That's what I mentioned about isothermal expansion. If you are having your notebook and pencil, you can write down. In an isothermal expansion of air, the volume increases by 5%. I repeat, in an isothermal expansion of air, because air means again a gas, the volume increases by 5%. The percentage change in pressure is, or what is the percentage change in pressure? So it is isothermal change, and because it is an isothermal change, we use the formula like PV is equal to a constant. Based on that, you can think of this problem. And on the other hand, the equation of state corresponding to 7 gram of nitrogen is, assume nitrogen to be an ideal gas. Assuming that nitrogen to be an ideal gas, what is the equation of state corresponding to 7 gram of nitrogen? That means here we have to relate what is called the molar specific heat and the other one. And let me give you one more problem. The pressure and the density of monoatomic gas. Anyway, I didn't talk about the monoatomic, diatomic, and polyatomic gas molecules. And in respect of monoatomic, like helium, neon, they are all monoatomic gases. In other words, what is that? Neon, xenon. They are all what is that? Monoatomic gases. And diatomic, you can think of nitrogen, oxygen, or anything. Polyatomic, carbon dioxide, something like that. The value, of course, you know that. I'm not going to tell you all those things, but it's only a problem. And the pressure and the density of a monoatomic gas suddenly changes respectively from pressure P1 to P2 and density ρ1 to ρ2. And what is the value of the pressure P2? This is another problem. And for example, if I take one more problem, it is like this. When the temperature of a gas filled in a closed vessel is increased by 1 degree Celsius, its pressure increases by 0.4 degrees Celsius. The initial temperature of the gas. What is the initial temperature of the gas? This is what I hope you have some problems like this. Better you calculate. And one more problem I can just suggest is 1 mole of a gas at NTP. NTP means normal temperature pressure is suddenly expanded to 4 times its initial volume. If Cv is equal to 2R, then what is the final pressure of the gas? So this is what some typical numerical problems in this thermal expansion. Of course, the coefficient of linear expansion, let us say L1 is given. You can remember the formula like alpha is equal to L2 minus L1 over L1 into T2. So I suppose if I keep on doing, I don't know whether they permit me or not. I think I will go for this. And thank you. If you have any clarifications or problems, you can ask me now. Yes, sir. Let them ask few questions if they have.
Thank you, sir.
Anybody has sent any question?
Dear students, please ask any doubts and any questions on today's topic. ಏನೇ ಡೌಟ್ಸ್ ಇದ್ರು ಸರ್ ಈಗ ಎಲ್ಲ ಇದ್ದಾರೆ.
ಕ್ವಶನ್ಸ್ ಕ್ಲಾರಿಫಿಕೇಶನ್ಸ್ ಅಥವಾ ಇನ್ನೇನಾದ್ರೂ ಈ ಟಾಪಿಕ್ ಗೊತ್ತಾಗ್ಲಿಲ್ಲ, ನೀವೇನೋ ಹೇಳಿದ್ರಿ ಸುಮ್ಮನೆ ಹೇಳ್ಕೊಂಡು ಹೋಗ್ಬಿಟ್ರಿ ಅಂತನೋ ಏನ್ ಬೇಕಾದ್ರೂ ಕೇಳ್ಬೋದು. ಅದಕ್ಕೆ ತಕ್ಕ ಮಾಹಿತಿನ ಕೊಡ್ತೀನಿ.
ಸೊ ಚಾಟ್ ಬಾಕ್ಸ್ ಅಲ್ಲಿ ಯಾವ್ದೇ ಕ್ವಶನ್ಸ್ ಇಲ್ಲ ಸರ್, ಹಾಕಿಲ್ಲ.
ಹೌದಾ?
ಸೊ ಲೇಟರ್ ಆನ್ ಅವ್ರು ಯಾರು ಕ್ವಶನ್ಸ್ ಕಳ್ಸಾರ ನಾನು ಐ ಸೆಂಡ್ ಥ್ರೂ ಮೇಲ್ ಸರ್.
ಓಕೆ ಸರ್, ಓಕೆ ಓಕೆ
ವಾಟ್ಸ್ಆಪ್ ಆರ್ ಸೆಂಡ್ ಥ್ರೂ ಮೇಲ್. ಸೊ ಲೇಟರ್ ಆನ್. So anyway, thank you, sir. It's an immense pleasure to thank you, sir.
Oh, thank you, sir. Thank you. Thank you.
So today's delivered talk on thermal properties of matter is very informative to students. So ಹಲವಾರು ಮಾಹಿತಿಗಳನ್ನ ಈ ಒಂದು ಉಪನ್ಯಾಸದ ಮೂಲಕ ವಿದ್ಯಾರ್ಥಿಗಳಿಗೆ ತಿಳಿಸ್ಕೊಟ್ಟಿದ್ದೀರಿ ಸರ್. ಸೊ ಮುಂದಿನ ತರಗತಿಗಳು ಕೂಡ ನೀವು ಮತ್ತೊಂದು ಉಪನ್ಯಾಸವನ್ನ ಒಂದು ಟಾಪಿಕ್ ಮೇಲೆ ಕೊಡಿ ಅಂತ ಕೇಳ್ಕೊತಾ.
ಓ ಖಂಡಿತ ಸರ್, ಖಂಡಿತ. ಥ್ಯಾಂಕ್ ಯು ಸರ್.
ವೈಯಕ್ತಿಕವಾಗಿ ಹಾಗೂ ನನ್ನ KSTA ಪರವಾಗಿ ಧನ್ಯವಾದಗಳು ಸರ್.
I thank you, sir. I thank you. Then I thank Dr. Ramesh, Chairman Ayyappan, and thank you all the members in KSTA, Karnataka Science and Technology Academy. In fact, I had come there 2-3 times. I know all of you. Therefore, I thank each one of you in KSTA. Thank you, sir. Thank you for the opportunity given to me to talk to students through you. Thank you, sir. ತುಂಬಾ ಧನ್ಯವಾದಗಳು ಸರ್.
ಸೊ ಅದೇ ರೀತಿ ನಮ್ಮ ಅಕಾಡೆಮಿ ಅಧ್ಯಕ್ಷರಾದಂತ ಪ್ರೊಫೆಸರ್ ಅಯ್ಯಪ್ಪನ್ ಸರ್ಗೂ ಕೂಡ ಧನ್ಯವಾದಗಳನ್ನು ತಿಳಿಸುತ್ತಾ, ಹಾಗೂ ಈ ಒಂದು ಕಾರ್ಯಕ್ರಮವನ್ನು ಆಯೋಜಿಸಿ ನಮಗೆ ದಿನನಿತ್ಯವೂ ಸಲಹೆ ಸೂಚನೆಗಳನ್ನು ನೀಡುತ್ತಾ ಬರುತ್ತಿರುವ ನಮ್ಮ ಅಕಾಡೆಮಿಯ ಮುಖ್ಯ ಕಾರ್ಯನಿರ್ವಾಹಕ ಅಧಿಕಾರಿಗಳಾದಂತಹ ಡಾಕ್ಟರ್ ರಮೇಶ್ ಸರ್ಗೂ ಕೂಡ ಧನ್ಯವಾದಗಳು. ಹಾಗೂ ಇಂದು ನೆರೆದಿದ್ದ ಹಾಜರಾಗಿದ್ದ ನನ್ನ ಎಲ್ಲ ವಿದ್ಯಾರ್ಥಿ ಮಿತ್ರರಿಗೂ ಹಾಗೂ ನನ್ನ ಸಹೋದ್ಯೋಗಿಗಳು ಹಾಗೂ ನನ್ನ ವೆಬೆಕ್ಸ್ ಬಂಧುವರಿಗೂ ಕೂಡ ಧನ್ಯವಾದಗಳನ್ನು ತಿಳಿಸುತ್ತಾ ಈ ಒಂದು ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮವನ್ನು ಮುಗಿಸುತ್ತಿದ್ದೇವೆ. ಒನ್ಸ್ ಅಗೇನ್ ಥ್ಯಾಂಕ್ ಯು ಸರ್.
Oh, thank you, sir. Thank you. Thank you, sir.
ಸೊ ಮಕ್ಕಳು ಕ್ವಶನ್ಸ್ ಕಳ್ಸಿಕೊಟ್ರೆ ನಾನು ಲೇಟರ್ ಆನ್ ಐ ಸೆಂಡ್ ಥ್ರೂ ಮೇಲ್ ಸರ್.
Okay, sir. ಆಯ್ತು, ಕಳ್ಸ್ಕೊಡಿ.
ಮತ್ತೆ
Okay.
ವಿದ್ಯಾರ್ಥಿಗಳಿಗೆ ಒಂದು ಸೂಚನೆ ನೋಡಿ, ತಜ್ಞರು ಕೊಡುತ್ತಿರುವ ಪ್ರಶ್ನೆಗಳಿಗೆ ಯಾರು ಸರಿಯಾದ ಉತ್ತರಗಳನ್ನು ಬರೆದು ಕಳಿಸುತ್ತಿಲ್ಲ. ಸೊ ಇದು ಬಹಳ ವಿಷಾದನೀಯ. ಸೊ ಇವತ್ತು ಕೂಡ 2 ಕ್ವಶನ್ಸ್ ಕೊಟ್ಟಿದ್ದಾರೆ ನನ್ನ ಚಾಟ್ ಬಾಕ್ಸ್ ಮತ್ತೆ ನಿಮ್ಮ ಗ್ರೂಪ್ ನಲ್ಲೂ ಕೂಡ ನಾನು ಸೆಂಡ್ ಮಾಡಿದ್ದೀನಿ. ಸೊ ದಯವಿಟ್ಟು ಇವತ್ತು ಯಾರೇ ಹಾಜರಾಗಿದ್ರೆ ವಿದ್ಯಾರ್ಥಿಗಳು ಅವರು ತಪ್ಪದೆ ಕಡ್ಡಾಯವಾಗಿ ಒಳ್ಳೆಯ ಉತ್ತರಗಳನ್ನು, ಉತ್ತಮ ಉತ್ತರಗಳನ್ನು ಬರೆದು ಕಳುಹಿಸಿ ತಮ್ಮ ನಗದು ಪ್ರಶಸ್ತಿಗಳನ್ನು ತಮ್ಮದಾಗಿಸಿಕೊಳ್ಳಬೇಕೆಂದು ಮತ್ತೊಮ್ಮೆ ಅಕಾಡೆಮಿ ವತಿಯಿಂದ ತಿಳಿಸಿದೆ. ಥ್ಯಾಂಕ್ ಯು ಸರ್. ಥ್ಯಾಂಕ್ ಯು ವೆರಿ ಮಚ್.
Oh, thank you, sir. Thank you.
ಥ್ಯಾಂಕ್ ಯು.
Fantastic, sir.
Ah.
Very good. Excellent. Beautiful.
Oh, thank
Whatever
you.
it is.
Hmm.